Hi everyone, welcome back to the channel. Today we'll be talking about one of the most crucial components of the training process for machine learning models, optimizers. Optimizers are the algorithms that determine how the weights of the machine learning model are tuned during backpropagation. It doesn't matter if we're talking about a neural network or something much simpler such as a linear regression model. Now, you're probably already familiar with optimizers even if you didn't think so. If you've heard of stochastic gradient descent, then you've already heard of the simplest optimizer there is. But there is one optimizer in particular that's revolutionized the ML community, ADAM, or adaptive moments. The original paper has been cited 176,000 times since it was published in 2015. Also in 2018, a new paper was published that corrected a small issue with the proof from the original paper and shared its own variant of the ADAM optimizer titled RMSprop. Needless to say, the ADAM optimizer is incredibly powerful, and it, or some variation of it, is typically the optimizer of choice when training modern ML models, including LLMs. After this video, you'll understand what exactly is going on in this animation, the math behind each of those optimizers, and how it applies to training ML models in real-world scenarios, such as classifying images or training a reinforcement learning agent. Towards the end, we'll also take a look at the latest papers on optimizers and what their recommendations are. For those of you that might need a quick refresher, let's quickly review how a machine learning model is trained from start to finish. First, we pass in our input data to calculate the predicted value of the model. This process can differ based on the model used. Then, the loss is calculated by comparing the predicted output with the ground truth, which is included as part of the training dataset. Take a look at this 3D graph, which shows an example loss function. For any two values of W1 and W2, which are the parameters of our model, we get a loss, represented by the height of this function at that point. Let's say the current parameter configuration places us here on the loss function. The lower the loss, the better, as that indicates our model can more accurately predict the data. This means our goal is to choose the values of W1 and W2 that land us at the star, or the minimum, of the loss function. As a side note, while this model only has two parameters, most linear regression models can have tens or hundreds of parameters. Neural networks can have billions. Obviously, visualizing the loss at such high dimensions is simply impossible. After we have our loss, we calculate the gradient of the loss function with respect to each of the model's parameters. The gradient of a function at any given point is the vector that points in the direction of steepest ascent. To go downhill, we multiply this vector by -1, giving us the direction of steepest descent. Nudging our parameters in this direction will reduce our loss just a bit. The gradient vector changes based on the loss function and what the values of W1 and W2 are. I've normalized the gradient vector to always be of length 1, which is why it has a constant length. But the key thing to note is that no matter where the loss is, the negative gradient always points directly downhill. That's why calculating this vector is so important in reducing our loss. If you need a more in-depth overview of how the gradients are calculated, I highly recommend checking out 3 Blue 1 Brown's machine learning series or Artem Kirsanov's video about backpropagation. Going back to the first animation, we multiply the gradients by our learning rate, sometimes referred to as alpha, and subtract the product from the parameters, essentially updating them. This means our loss takes a little step downhill, albeit not necessarily directly towards the loss's minimum. The size of this step is proportional to the gradient at that point, which is why the arrow shrinks as we approach the minimum. The loss function is less steep in that area. The intent here is that repeating this simple process thousands, millions, or billions of times will result in the loss of our model being minimized, or in other words, the star at the bottom being reached. But you might be asking yourself, Soresh, where do optimizers come into play? Well, take a look at that final step. We're using the optimizer that most students are introduced to ML with, Stochastic Gradient Descent. The SGD optimizer simply takes in the gradient, multiplies it by the learning rate so we don't take too large of a step, which might make us miss convergence, and just subtracts that product from the parameters. As we just saw, that is a visual equivalent of taking a step downhill in our loss function. This optimizer usually works and may or may not lead us to a set of parameters that optimally predict the labels of any piece of data that's fed into the model, assuming the training data is good and the learning rate isn't too large. But take a look at all of the steps SGD has to take to minimize this loss function, not to mention the fact that these steps take our loss on a detour to the minimum. Each step requires extra computation, so it'd be nice if we could take less steps overall and travel more directly to the bottom. This is exactly where more advanced optimizers such as SGD with momentum RMSprop, and the most iconic one of all, the atom optimizer come in. Each performs some nifty mathematical tricks with the gradients before updating the parameters to ensure convergence at a much faster pace, minimizing our loss function with less steps. This is really important, especially given the large prevalence of machine learning in our society. One result of efficient ML training that people often overlook are its environmental impacts. More efficient optimizers mean faster training, which means less electricity used, ultimately benefiting the environment. I mean, think about the cute little penguins. Also, let's not forget that efficient training supercharges innovation in any field ML has permeated, as now we're better able to iterate on our models at a much faster rate. Let's start by talking about momentum. Taking another look at vanilla stochastic gradient descent, the first thing we notice is that the ball's pace slows down pretty quickly, needing a lot of steps to reach the star. What if there was a way to speed things up? Thankfully, that's where momentum comes in. The easiest way to think about momentum is to literally think about momentum. I mean, from physics. When a ball rolls down a hill, it doesn't do so at a constant velocity. It gains speed as it travels down the hill, leading to it reaching the bottom much faster than a theoretical object with a constant velocity. The intuition SGD with momentum gains from physics is that if multiple steps of gradient descent are all in the same direction, we should feel a little more confident in taking larger steps, hoping that it brings us to the bottom of our loss landscape faster. It achieves this by comparing the direction of the current gradient with the ones in the past to determine the shape of the path gradient descent is taking. The straighter the path is, the larger steps we should take. Again, to emulate a ball rolling down a hill that builds up momentum. Here is a quick animation that compares traditional SGD with momentum. As we can see, momentum allows the loss to take larger steps towards the minimum. Yes, it does overshoot it by a little bit and has a spiral back, similar to how a ball would behave were you to roll it down this very hill. However, having momentum clearly beats vanilla SGD, even at the same learning rate. SGD gets really slow towards the end because the gradient is almost flat. It's scenarios like these where momentum can really shine. Let's dive into the math now. Recall that in vanilla SGD, we simply multiply the gradients by a learning rate and then subtract it from the parameters. I'll be using W to represent a generic weight or parameter of an arbitrary model. If we were to use this equation for our animation, we would have to update the W1 and W2 parameters, each with their own equation similar to what's on screen. Also, don't forget that nabla W is actually the gradient of the loss function with respect to the arbitrary weight W. These are the equations for SGD with momentum. Momentum is implemented mathematically by adding a portion of previous gradients to the current one before updating the parameters. We introduce a new term V, which you can think of as velocity, and a beta hyperparameter, which controls how influential past velocities will be in the current update. It's common for beta to be 0.9. A beta of 0 would result in vanilla SGD. We multiply the new gradient by 1 minus beta and the old velocity by beta, giving us the new velocity term. We then multiply this new velocity term by the learning rate and then subtract that product from the parameter values. This equation is essentially taking an exponentially weighted average of the gradients, with more recent ones given a larger weight, which means that they're multiplied by beta less times. If we unroll the above equation, we see how this is so. V sub t plus 1 is a function of V sub t. V sub t is a function of V sub t minus 1, and so on and so forth. All I'm doing on screen is replacing each V term with the full equation for velocity and distributing the betas. Looking closer, the older a gradient is, the higher the exponent of the beta it's being multiplied with is. Since beta is always less than 1, this assigns a smaller weight to older gradients. For momentum, since the hyperparameter beta and the learning rate both affect the likelihood of convergence, it's more typical to just tune the learning rate and keep beta at 0.9. For this video, my goal isn't to showcase the effect of the learning rate on convergence. I hold the learning rate constant to showcase the differences between SGD and SGD with momentum. Obviously, SGD with an optimal learning rate will always beat out SGD with momentum with a learning rate that is magnitude smaller, but that wouldn't be an apples to apples comparison. However, since momentum introduces a higher possibility of overshooting a minima, which might slow down convergence or possibly even prevent it, We want a way to rein in the updates. If the learning rate is a little bit too high, the loss has to circle back, wasting extra steps. And if the learning rate is way too high, then the loss will just explode and never converge. NAG, or the Nesterov Accelerated Gradient, is an optimizer that addresses this issue. Momentum's update step can be broken into two parts: a small step in the direction of the gradient at the current position, plus the accumulated gradients from the previous steps. NAG, on the other hand, first takes a step in the direction of last iteration's update, and then a small correction step. Adding these two steps together yields us our update for the current iteration. It's assuming that the gradient in the current iteration is in a similar direction as the gradients from the previous iterations, plus the small correction. The goal is to still have some sense of momentum, but one that's slightly more controlled and directed. This is what momentum and NAG look like with the same learning rate and beta hyperparameter. We see that NAG reaches the minima faster in this example, but note that this may not always be the case. Results may vary depending on the specific problem domain. I'm not going to dive deeper into NAG in this video, but I just wanted to put it on your guys' radar should it pique your interest. If you wanted to use SGD, Momentum, or NAG as your optimizer, they're all under the SGD class in PyTorch's Optim module or TensorFlow's Optimizers module. Momentum can be a game changer, but there are additional characteristics of loss functions that might work against us. Take a look at this following function. It's just a parabola in 3D, but the bottom isn't perfectly flat. There's a slight decline towards the center. Here, SGD is simply too slow, and momentum is all over the place. Both optimizers take a huge detour to the star. The reason for this is because the gradient of W1 is much greater than the gradient of W2 at the starting location, due to the gradient pointing predominantly in the W1 direction. This causes the algorithm to first optimize one parameter and then the other. The issue with that is as the loss approaches the bottom of the valley, the path to the center is almost flat, leading to really small gradient updates. Remember the equation for gradient descent, where we multiply the learning rate by the gradient before subtracting it from the old parameters. Small gradients mean small updates. Loss landscapes similar to this one emerge when we have sparse data. Maybe some feature column is mostly zeros, but when it's not, it holds a lot of information that we want to be able to utilize maximally. It'd be nice if we were able to take larger steps in the W2 direction and slightly smaller ones in the W1 direction. Is there another optimizer that can help us with this? Enter RMSprop, or root mean squared propagation. The main feature of RMSprop is that it's able to adapt the learning rate separately for each parameter. It should be noted, however, that it's not the first optimizer to introduce this concept and actually pulls the idea from AdaGrad, or adaptive gradients. Let's take a look at how RMSprop handles this loss function. Wow, looking at the path it takes tells us that it's able to optimize both parameters simultaneously, rather than the one with the larger gradient first. That means RMSprop is able to accommodate for the difference in the gradient size across parameters. Let's dive into the math to truly understand what's going on. Once again, we have a velocity term that we first calculate, just like with momentum. We also have a hyperparameter beta. The old velocity term is multiplied by beta, and the square of the gradients is multiplied by 1 minus beta. Afterwards, the two products are added. Finally, when we update the parameter, we multiply our learning rate by this weird looking fraction. In the numerator, we have the gradient. In the denominator, we have the square root of our v term plus epsilon, which is another hyperparameter, but is pretty much always kept to a really small number like 1 to the negative 8th power. The point of it is to avoid a divide by zero error. That fraction helps modulate the learning rate based on the parameter's gradient. For parameters that have a history of larger gradients, the denominator will be larger, resulting in a smaller update. Smaller gradients won't be affected by this as much. This allows the rate at which parameters with larger gradients are updated by to be dampened relative to parameters with smaller gradients. Remember why this is so important. In loss functions like this one, where one parameter's gradient dominates the other ones, having some sort of normalization force balancing the varying sized gradients results in a more direct path being taken to the minima. Like I mentioned earlier, RMSprop builds upon an optimizer that came before it, named AdaGrad, or adaptive gradients. Both optimizers modulate the learning rates for each parameter separately, but AdaGrad doesn't weight down older gradients. It simply adds up the square of all the past gradients and takes the square root. That means as training progresses, the denominator continues to grow and grow, leading to the learning rate progressively getting smaller and smaller. hindering AdaGrad's ability to converge. RMSprop alleviated this issue by introducing the exponentially weighted average, another optimizer that was developed independently of RMSprop to address the issue of AdaGrad is named AdaDelta. AdaDelta limits the number of past gradients that are included in the calculation of how to modulate the learning rate. Again, I won't be diving deeper into AdaGrad and AdaDelta in this video, but simply wanted to let you guys know that they exist. That was a lot, but I hope you're as excited as I am to find out that SGD isn't our only option when it comes to optimizers for our ML models, because my goodness, that thing can be slow. Using momentum and adaptive learning rates allows our loss function to be optimized more efficiently. But you might be at the edge of your seat eagerly asking, what happens when we combine the two? Well, that's where ADAM or adaptive moments comes in. The first moment is typically referred to as the mean, which makes sense in the case of momentum because if the magnitude of the mean is higher, that indicates the gradients are pointing in the same direction. The second moment refers to variance, or squared error, which is what RMSprop uses to modulate the learning rates individually for each parameter, based on its gradients. Just a technical note though, it's not exactly variance that we're calculating, but rather the uncentered variance, because we're not subtracting by the mean. In cases with higher variance, we want to take smaller steps, and be more confident by taking larger ones when the variance is lower. Let's first take a look at what ADAM can do. We've defeated the first several cost functions with ease, but now it's time to face the boss cost function. The defining characteristic of this loss function is that it has two minima, one local and one global. We want our optimizers to find the global minimum because the lower the loss, the more accurate our model is. As our optimizers start optimizing, we see something fascinating. ADAM, with its momentum and adaptive learning rates, goes into the crater with the local minima but is able to escape it. Then it finds the global minimum way before traditional SGD even reaches any minima. This strength of ADAM can also be a weakness, however. If the learning rate is too high, it might overshoot the global minimum and land in a local one. That's why it's the task of the machine learning scientist to properly tune the hyperparameters. Here's the animation again, but this time with all four optimizers. The ADAM optimizer beats out the other three. RMSprop goes directly towards the center, but gets stuck at the local minima. SGD with momentum starts off in the similar direction as SGD, but takes a faster, albeit windier path to the local minima, again missing the global one, and poor SGD is still dead last. I do admit that this is a contrived example, but we'll see how these optimizers fare in real-world scenarios in just a bit. Let's quickly take a look at the equations for the ADAM optimizer. You should find the first two very similar for momentum and RMSprop. The exact same intuitions apply here. But we introduced two new equations after that to account for bias correction, represented by m hat and v hat. Bias arises because both m, the estimate of the first moment, and v, the estimate of the second moment, are initialized to 0 at the start of training. Consequently, at the beginning, we're essentially scaling down the gradients significantly due to the formula involving beta for m and v being multiplied by 0, and 1 minus beta by the new gradients. Given that beta 1 and beta 2 are typically set to 0.9 and 0.99 respectively, it inherently delays the impact of new gradients on the optimization process. The bias correction equations for m hat and v hat help mitigate this issue, ensuring that the gradient estimates don't get overshadowed by m and v being initialized to 0, which helps tremendously in the initial phase of the optimization. As training goes on, the exponent and the denominators continue to increase, leading to the denominator approaching 1, nullifying its effects. These bias terms would be helpful for SGD with momentum and RMSprop as well, but they're not typically used. So the outcomes I've shown you so far can vary wildly depending on the loss function and the learning rate that are assigned to each optimizer. The animations I've shown were cherry-picked to best outline the strengths and weaknesses of each optimizer. But don't worry, that's why we'll now be taking a look at some benchmarks to truly see the impact each optimizer has on performance and training time. Also, I've performed some tuning for the learning rate to make sure each optimizer has a fighting chance, but all the other hyperparameters have been kept their default values. First, let's start off with the fashion MNIST dataset, where the task is to correctly predict the label of these clothes. The first graph shows the training loss over 10 epochs of training for each optimizer. The results are what we expected, with ADAM and RMSprop performing much better than SGD and SGD with momentum. This is also apparent when we look at how the test accuracy increases over time. Looking at this paper, which did a meta-analysis of the various optimizers, we see that they also have similar results, with ADAM just barely beating out RMSprop in 2 2 of their 3 convolutional neural networks, and Momentum and SGD doing much worse. Just to note, they used the original MNIST dataset. This second meta-analysis also yielded similar results. They used the Fashion MNIST dataset, again with a CNN, and we see that test error was minimized with RMSprop, Adam, and the NADAM optimizers. Now let's take a look at the ResNet 18 model. I just pulled the model architecture from TorchHub and used the SciFar 10 training dataset. As we can see here, Adam once again is king. This is the graph of train loss, and this is the graph of test accuracy. Going back to the first meta-analysis, we see that Adam has a slightly larger lead over RMSprop with the SciFar 10 dataset across all 3 model architectures. It seems that the AdaMax optimizer did the best, which I encourage you guys to look further into. These are the results from the second paper with the ResNet 32 and ResNet 50 architecture with the SciFar 10 dataset. This paper, which performed image classification on wildlife animals to compare the Adam and RMSprop optimizers, once again, also has similar results to what we've seen so far. The mean accuracy of 2 of the 3 models at a learning rate of 0.001 was higher with Adam. Next, let's revisit the world of reinforcement learning. Training my Super Mario Bros. Agent with each optimizer would take too long, so I've chosen a simpler environment and reinforcement learning algorithm. We're using a very simple implementation of the policy gradients algorithm with the Pong environment. If you really enjoyed my previous DDQN video and want to learn more about policy gradients, stay tuned because I have a video that's currently in the works on that. On screen, our agent is on the right in green. Taking a look at the results, I noticed that there was a lot of run-to-run variation. The first time, we see that RMSprop beats out Adam, with SGD and Momentum trailing behind, but in a second test run, Adam was actually the winner. I've done some research on this topic and I've seen reinforcement learning papers use both Adam and RMSprop. We've already discussed why Adam might be better because it combines both momentum and adaptive gradients, but one theory behind why RMSprop might be better, specifically for reinforcement learning, is the following. As our agent explores new areas of our environment, the distribution of training data tends to shift. What used to be the best action towards the beginning of the game may not remain the case later on in the game. This means that samples in reinforcement learning are not independent and identically distributed. In such cases, momentum may actually be a detriment to performance due to samples throughout training potentially varying wildly from each other. Looking at not just my experiment results, but also those of research papers, I think one thing holds true. While Adam is a good starting point, it definitely is not the end-all be-all of optimizers. Different optimizers may shine in different scenarios, so always be open to experimentation. I hope now you guys see the true importance that optimizers have on the machine learning training process. They can literally make or break your training. Having a thorough understanding of how these optimizers work is a non-negotiable prerequisite to understanding how other aspects of ML work, such as large-scale distributed training. One final thing I want you guys to think about. Take a quick second and try to imagine which of these optimizers take up the most memory while training. Think about how many extra values each optimizer requires for each parameter. If you thought of Adam as being the most memory inefficient, you're right. For each parameter, we're storing 2 extra values, essentially tripling our memory usage. When using multiple graphics cards to train multi-billion parameter models, it's important to minimize memory usage across all the GPUs, along with minimizing communication between the GPUs. That's where libraries like Microsoft's DeepSpeed with its zero redundancy optimizers comes in. It cleverly splits up all the optimizer states across the GPUs in such a way that training large LLMs can experience a speedup of around 300%. Unfortunately, diving into the DeepSpeed library is out of the scope of today's video, but I just wanted to share a quick example of why understanding optimizers is so crucial. If all that sounds interesting to you, let me know and I'd love to make a video about it. However, thank you guys for making it until the end, and until next time, bye-bye.